Hey, welcome to the ECU Academy.
Today we're going to teach you some Riemann sums and the trapezoidal rule.
That's Jacqueline. And that's Melody. And I'm Claire. Stay tuned.
Am I in it?
Riemann sums will help us to estimate the area under a curve. And they were created by this guy, Bernard Riemann. It's pretty cool, even though his glasses are crooked. We're going to use a left Riemann sum to estimate the area under the graph x squared. First, we're going to need to split up our graph into rectangles, but we're going to do this by using the left side of all of the measurements we've already taken. So here is x equals 0, and at x equals 0, the function equals 0. So there isn't a rectangle because there's no height since we're using this left endpoint. Now let's move to x equals 1. At x equals 1, the graph equals 1, so the height of the rectangle will be 1. And we'll continue doing that throughout the whole graph. So at x equals 2, it equals 4. So the height of this rectangle is going to be 4. Just keep doing that, drawing from the left side over. So you have all of these rectangles shaded in. That's going to be our estimate for this graph. So in order to estimate this area, you have to know that the area of a rectangle equals base times height. For this graph, all of the heights equal 1 because that is the width that we chose, which is usually the best idea if you're going to find a Riemann sum, is to use equal widths for all of your rectangles if that's possible. Now, in order to find the area under the graph, we're going to need to add up the areas of all of these rectangles. So in order to do that, we're going to multiply the heights of all the triangles times the bases of all the rectangles. Rectangles. So since all the heights are the same, we can put the height of all the rectangles outside of the addition problem. So this is our height, because it's all 1. And now to multiply all of the measurements together. So you're going to have f of 0, since that's the first left side, plus f of 1, plus f of 2, and so on. Okay, now you need to go to your graph, or table if that's what you're using, and find all of these measurements. At f of 0, it's 0, f of 1, and so on. And now all you have to do is add these up. And when you do that, you get 55. And since now we would multiply it by the height, but since it's 1, it's going to stay 55. And there you have it. That's your left estimation. However, you will see this estimation is an underestimate because we have excluded all of these areas from our estimation. So in reality, the actual area under this graph is more than 55.
Approximating from the right endpoint is very similar to the left. However, we will start from the right endpoint of the rectangle. And for example, we will be approximating the area underneath the graph of x squared. So from here you can see the right endpoint is above f of 1, which is 1, 2, which is 4, f of 3 is 9, and so on and so forth. And so with the equation a equals base times height, we will start with the height, which for each one, they're all 1, multiplied by f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5, and then f of 6. And so from the graph you can see that f of 1 is 1, f of 2 is 4, then 9, 16, 25, and 36. And when you plug all of this into your calculator, you will get an answer of 91. In order to get a more accurate estimate, we could also use the midpoint RAM which means that our height will still be the same, but instead of using the left endpoint or the right endpoint, we will use the midpoint, which is much more accurate than the other two. So you'll go in between both sections, and you can see that this area, which is over the curve, will cancel out the area that is underneath the curve, making it, again, more accurate. And so our height, or our delta x, is still 1 throughout all of this. So multiply the outside by 1, and then you will take the f of whatever the midpoint is. So for example, first one will be f of 0.5 plus f of 1.5 plus f of 2.5, and so on. F 3.5 plus f of 4.5 of 5.5. That's the last one. Where's my sheet? Pause. And when you punch these in your calculator, you'll see that this equals 0.25, 2.25, 6.25 plus 12.25 plus 20.25 plus 30.25, and all of that equals 71.5.
So like the Riemann sums, trapezoidal rule is also used to find the area under a graph, but it's much more accurate because you can make the top slanty to fit the graph. So instead of making this a rectangle, you go like this, and you make just a bunch of trapezoids. And it's much more accurate to find the area. So this is your height, and then you have all of your bases. So B1, B2, B3, B4, and B5. So you can pause it now. So what you're going to do is find the area of each trapezoid. If your heights for each trapezoid are different, what you do is you add them all separately. So your area of a trapezoid is 1/2 times h, and then your bases, so B1 plus B2. And then you're going to add it to the second trapezoid, so 1/2 times h, which is going to be this height, B2 plus B3. I'm going to do that till you have all your trapezoids, B3 plus B4, and 1/2 h, B4 plus B5. Now you also might have it where all your heights are the same, in which case you can consolidate it and do it all at once. So in that case it would be 1/2 times height, and then times all of your bases. So it would be B1, and then like you saw here, when your h's were different, you used each base twice except for the first and the last one. So you can have B1 plus 2B2 plus 2B3, etc., until you get to your last base. So you might not know what your height is, so what you're going to do is h equals, you see your two endpoints, so b minus a over n, and n is the number of trapezoids. So then when you translate that into your formula, your final formula for the trapezoidal rule is going to be 1/2 times b minus a over n times f of x 0, which is going to be, this is x 0, and b1 is basically the same as f of x 0. So f of x 0 plus 2 f of x 1 plus 2 f of x2, etc., until you get to your final f of x. So f of x n, back to the n from the height. And that's your trapezoidal rule formula. So we're going to use the trapezoidal rule to approximate the area under the graph of x squared. So you don't always have to do this, but it's helpful if you draw it out to have a visual. So you draw out your trapezoids. See how it's much more accurate than the rectangles with the Riemann sums. And if you remember our trapezoidal rule formula, so you're just going to plug in everything with 6 as your b, and your a is 0, And you have 6 rectangles, so 6 is n. And your f of x of 0 is your first one, so that's 0. So you have f of 0 plus 2 times f of 1 plus 2 times f of 2 plus 2 times f of 3, 2 times f of 4, 2 times f of 5, and then plus f of 6. Then you're going to simplify that, so you have 1/2 0 plus 2 times 1 plus 2 times 4 plus 2 times 9 plus 2 times 16 plus 2 times 25 plus 36. Now if you plug all that in, you're going to end up with an answer of 73. So we are going to send you away with a couple of example problems to work out on your own. First, you're going to find the area underneath the graph of sine of pi x over 4 using a right Riemann sum and the trapezoidal rule. Pause this video, work it out, and then we'll show you the answers. So if you worked it out right, for the right Riemann sum, you should have gotten an answer of rad 2 plus 1. And for the trapezoidal rule, you should have gotten an answer of 2 rad 2 plus 2.
We'll leave you with a second takeaway problem for you to do and work out on your own. Using the function f of x equals negative 1/2 x squared plus 15, and on the interval 0 to 5, estimate the area under the curve using a left Riemann sum and a midpoint Riemann sum. Pause the video now and work out the solution and find your own answer. We'll come back in a second to tell you what we got. Okay, now that you've worked out the problem, you should have gotten 60 for using the left point and 54.375 using the midpoint.
Hey, thanks for watching our video.
We hope you learned something.
Math is really fun. You'll get a 5 on the AP test. We know it. We believe in you. Bye.
When you're buying router bits for the shop, here's what I want you to do. Whenever possible, get yourself a 1/2-inch shank router bit instead of a 1/4-inch shank. Right here on the table, I've got 2 bits, identical profiles. They're both 1/4-inch round over, 1/2-inch shank, 1/4-inch shank. Now the deal is a couple of benefits here. One is that, of course, because the shank on a 1/2-inch shank bit is bigger, it's less likely to flutter under cutting pressure, which means you're going to get a better cut as a result of what you're doing with your router. The other thing is that because the diameter is bigger, the circumference is also greater. That gives your collet a much better bite on this router bit. As a result, it's much less likely to come loose. For the most part, what you'll find is that the 1/2-inch shank bit doesn't cost any more, or it's only a tiny bit more than the 1/4-inch shank, but you get a lot of benefits out of using it. The reason that you might choose to stick to a 1/4-inch shank bit would be if you're using something like a laminate trim router where you're limited to 1/4-inch shank cutters. But most mid-size and larger routers come with both a 1/4-inch and a 1/2-inch collet. They're capable of taking either one, and my advice to you is whenever you can, get the 1/2-inch shank bit for your machine.